Good afternoon. Welcome to AP Stats. We're going to talk a little bit about the homework that was due today. If you struggled with it a little bit, I'll give you another night. You can have till Thursday to work it out. But basically, that first homework problem, list one, if you struggled with it, take till Thursday. I'll still give you full credit. It's basically a one-way table. And since we're trying to find out whether or not the wording of it was, of the question was, determine if there's a convincing evidence that the good doctor is not correct in his assessment that had to do with, he said those responses look like they fit the binomial model. Well, the word fit is an indication that we're talking goodness of fit. We tried to throw you off a little bit by putting the one-way table laid out horizontally to somehow perhaps cause you to not realize that you have to enter them vertically into list one. So we got 1676, 1608, 587, 124, and 5. So those are the numbers you would put in list one. But then the question is, what are the expected values? It's not as easy as the example we did yesterday. When you roll a die 60 times, you would expect 10 in each. Here, you had to take the 4,000 items, which are distributed into list one, and use the binomial distribution 4, it was given as 4, 0.2, I believe. Yeah, 4, 0.2. So you had to remember row 4, Pascal's triangle, 1, 4, 6, 4, 1. And you also had to remember that to form this distribution, you'd have to take 1 times 0.2 to the fourth, or you could do 0.2 to the fourth or 0.2 to the 0. But interestingly, yeah, it looks like they fall off here. So it does really matter whether you start out with 0.2 to the fourth times 0.8 to the 0, or times 0.2 to the 0, 0.8 to the fourth. And it looks like since they're starting out big and getting small, we'd better set up 1, 4, 6, 4, 1 as follows. We'd better do 0.2 to the 0 times 0.8 to the first, because that looks like, 0.8 times 4,000 plus, and then 4 times, this is going to be 0.2 to the first, 0.8 squared, plus 6 times 0.2 squared times 0.8 squared, plus 4 times 0.2 to the third, 0.8 to the first. And, hold on a second. It's 0 and 4. So go 0, 4, then 1, 3, 2, 2, 3, 1, and this last one is going to be 0.2 to the 4. So which one is the biggest one? Interestingly, which is bigger, 0.8 to the fourth or 0.2 to the fourth? Because the last one is 0.2 to the fourth times 0.8 to the 0. 0.2 to the fourth is 2/10 to the fourth power. 0.8 to the fourth is 8/10 to the fourth power. Well, it seems like 8/10 to the fourth would be a bigger number because it starts out bigger, and if at any point it were ever the least bit confusing to you, you could always just go and check. 0.2 to the fourth compares how to 0.8 to the fourth. And sure enough, 0.8 to the fourth is a lot bigger. It's about 40%. And that is kind of like what it looks like here. It looks like this might be right about 40%. So it matters which way you go. You would want to do this number times 4,000 to get your expected value here. So if you're wondering what's the first number in list 2, it's 0.8 to the fourth times 4,000. What's the second number in list 2? It's going to be 4 times 0.2 times 0.8 cubed times 4,000. The third number in list 2 is going to be 1, 4, 6, 4, 1. This is 0.2 to the 0, 0.2 to the first, 0.2 squared, 0.2 cubed. It's all very systematic coming from the binomial distribution. It's going to be 0.8 to the fourth, 3, 2, 1, and 0, 0.8 to the 0. Then you can run a chi-squared goodness of fit test to get a p-value. So any questions on how to set up either list 1 or list 2 on that particular problem? Yes, go ahead.
How do you know that's how you set up list 2?
Well, because they told you that he's expecting these numbers to be distributed according to a binomial distribution with n equals 4 and p equals 0.2. That's given information. So that's what the binomial distribution of those numbers would be. I mean, these numbers in the binomial probability distribution all have to add up to 1. So that means you'll get 100% of the 4,000 using these numbers. Further questions? Yeah, so if you want to follow up any more on that, you can see me outside of class. The calculator activity I have for you today has to do with critical values, and in particular, critical values of a chi-square distribution. So, I would recommend that you hang out here, maybe find some blank space in comparing counts 2 of 3, which is yesterday's handout. This is the one that we left on at the end of class yesterday. And you probably have some blank space right there on page 1 in order to do this activity. So, let's talk about critical values. Critical values, that's implied of test statistics. What's the critical value of the test statistic? Well, Z is a test statistic. What's the critical value of Z? This will be our first example. What's the critical value of Z for a one-tailed test in which we have set alpha at 0.05? So if alpha equals 0.05, what would the critical value be? Basically, the critical value of Z, it's the value of Z above which we would reject the null hypothesis. Now, for what value of Z would I reject the null hypothesis if the normal model is the standard normal model with a mean of 0 and a standard deviation of 1? Well, that's what inverse normal is about. Inverse normal essentially can give you critical values if you know the alpha level. So we've done these sorts of problems before. Inverse normal of the left area for 0.05 would be 0.95. And so 1.645. So 1.645 is the critical number for if it's a right hand or upper tail test. Now, had it been a two-tail test, then that'd be a different story. If it were a two-tail test, then I'd have to put 2.5% in each tail and do inverse normal of 0.975. So it depends whether it's one tail or two tail. Well, the nice thing about chi-squared is that it's inherently two-tailed, but you only draw one tail. So for a chi-squared distribution, someone could ask the question, if you have a chi-squared distribution with 14 degrees of freedom, what would be the critical value of chi-squared if your alpha level is set at 0.05? Well, there's no inverse chi-squared button on the calculator. There's an inverse normal button, and there's an inverse t button, but there's no inverse chi-squared. So how are we going to basically pull off a problem where we need to find inverse chi-squared when there's no inverse chi-squared button? Well, here's how you do it. It's a trial and error process that doesn't take very long. What you do is you engage in the following trial and error activity. Let's do it all together on the calculator. Since there is no inverse chi-squared, here's how we roll. We first of all guess what it might be for 14 degrees of freedom. So we're going to go chi-squared CDF. We're going to add up all the area from some guessed value up to 999 with 14 degrees of freedom, and we're going to refine our guesses until we're accurate to 2 decimal places. This is what's going to be on the quiz. Okay. So you have to basically pull off an inverse chi-squared without the inverse chi-squared button. Now, some students look at tables. It's just, honestly, it's just way more fun to do it on the calculator. And by the way, the tables are just kind of cumbersome. Tables are old school, okay? I've said it. So, let's go chi-squared CDF. That's item 8, distribution item 8. So I don't know what, I'll guess 10. Let's go from 10 to infinity with 14 degrees of freedom. And okay, so it's 0.76. Wow, way too big. So you gotta ask yourself, do you really understand the logic of the chi-squared distribution? If 10 gave us an area of 0.76, and we want to get it down to 0.05, which way do I move? Do I move, well, I want less areas, so basically, should I pick for my next guess a number bigger than 10 or smaller than 10?
24.5. That's my guess.
Okay, so if chi-squared equals 10 gave us too much area, we need a bigger chi-squared test statistic in order to whittle this down to 0.05. So I do second enter to pull it up again, and we want to plan for 2 decimal places. Let's go 20 and then go insert 0.00. Okay, so get 2 decimal accuracy in there. 20 is going in the right direction, but it still needs to be bigger. So go
Wait.
second enter and keep editing this.
Mr. Royce.
Yeah.
How do you do insert?
Second INS.
The delete one.
Yeah, it's right above delete. So delete, insert. Okay, so that way you don't have to type over the whole thing. So Jeffrey apparently thinks it's somewhere around 24. Now, is 24 too big or too small?
It's too big.
Yeah, we went too far, so let's come back a little bit. See if you can get it to the nearest decimal. I guess 23.5 would be the next logical place to start. There we go. 5, that's a little bit too big. So there's too much area, So to ease it to the right. 6. Still too big, but I'm going in the right direction. 7. Ooh, 7?
6, 8.
So now I'm here. So I would probably go to, I'd go to 6.5 next. Try to go in the middle. And then, so I pulled it back to 6.5, that's too much. So now I need a number farther to the right to get less area. So I do 6.7, someone said 6.8. It's still technically, go 23.69, I come under. Okay, so it's somewhere between 0.68 and 0.69. So I would accept either of these. If this were a quiz, basically inverse chi-squared, the critical chi-squared value is, I would accept either 23.68 or 23.69. Here, you try one. What would be the critical chi-squared value if you set your alpha level at 0.03 and you're dealing with a chi-squared distribution with 8 degrees of freedom? Find on your calculator by trial and error the critical chi-squared value. Sometimes we would call it chi-squared star. Star is critical. Chi-squared star. Now, hopefully, you find both numbers that are on either side of the correct answer. Raise your hand when you found a fellow group member who agrees with the 2 numbers that are basically the bounds, the upper and lower bounds of the critical chi-squared. So if you find the upper and lower bound, the chi-squared, either of which would be a full credit answer, then collaborate with the group member. All right, has anyone found one of the chi-squared values, either an upper or lower bound? Yes. Amelia, go ahead.
16.959.
So 16.95 is a little bit more than 0.03. And what one do you think will be a little bit less than 0.03? Should I go to 9.4 or 9.6 so that it will be a little bit less than 0.03?
Me?
Yeah.
6.
And if you're not sure, the visual that will help you is that keep in mind we're currently at chi-squared equals 16.95, and we're getting an area of 0.0306, so it's a little bit more. So if you want less area here, should I move this chi-squared right or left?
Right.
Yeah, if you move it right, that should be a little bit less. So 16.96 should be, oh, it's still not under, so let me go 0.97. Let's see if that takes it under 0.97. We still got, moving to the right, it's still above. Notice it is coming down, 5, 4. So it looks like we have to go a ways. Who's found the largest number that still keeps it above 0.03? Ryan?
17.01.
Okay, so this is the kind of work you have to do. You have to make sure you actually find where the boundary is to the nearest tenth. So it's easy to get close, but to get accurate, Ryan thinks that's the last time that we're above 3. Once we go any farther to the right, we're gonna sink below 3. Let's see if he's right. Once we go to 17.02, yep, now we're on the other side. So that means the critical chi-squared value to 2 decimal places, I would accept either 17.01 or 17.02 on the quiz. Any questions on that? It's critical chi-squared value for alpha equals 0.03. Okay, so that's the warm-up activity. We went over the homework a little bit, and we're on the childbirth problem right when class ended yesterday. And let's see how far we made it. It looks like we're filling in the B values from matrix B. These were the expected values. We're trying to find out whether or not having an epidural is independent of whether or not the child is breastfeeding after 6 months. And in terms of the setup, we said there's 2 variables. Breastfeeding is categorical, either yes or no after 6 months. Having an epidural is either yes or no, so they're both categorical. We're going to perform a chi-square test for independence. And since this was right at the end of class yesterday, you might not have gotten this. I mean, this is the kind of stuff we'll be quizzing on you. Can you word the null hypothesis correctly? Can you express the wording on the alternate hypothesis correctly? Null hypothesis is that breastfeeding success is independent of having an epidural. No numbers. There's no numbers in there. It's just words. There is an association. So could you word it as breastfeeding success is not independent of having an epidural? Yes. But in a multiple choice setting, you would have to recognize that this is an accurate way to express the wording of the alternate. It's like, if they're independent, that means there's no association. We talked about that language in Unit 1 with the Titanic problem way back in August. So likewise, we can say, well, there is an association. Having an epidural and breastfeeding after 6 months, successful, they have something to do with each other. Now, in part 2, we refer back to exercise 13. The table shows the results of the study, whether the after effects of epidurals administered during childbirth might interfere with successful breastfeeding. We're planning to do a chi-square test. How many degrees of freedom? Okay, so we did do this yesterday. We calculated degrees of freedom. And I'm going to go fit to height, just make sure you can see this whole thing. Then we'll go back to fit to width. Okay. Yep. So you have that wording there. We're on page 3. This one is where you actually had to do the mechanics. So the mechanics, in part A, you said calculate the component. Yeah, those 4 numbers, there's 4 of these made up that have to be added together to get chi-squared. And they're checking to see, do you know how to calculate the components? So the one they asked about was the yes epidural, no breastfeeding cell. So yes epidural, yes, breastfeeding, okay, so for this cell. The vocabulary here is components. Chi-squared, since there's 4 cells, has 4 components. Each component is has the same formula, which we expect you to memorize and write down when you're documenting this. You have to show at least one component calculation so that we see that, observed minus expected, quantity squared over expected. So 190 minus 159.3, quantity squared divided by 159.3. That's the component. So in terms of new material, this is a new vocabulary term for today. CNTRB, I think that's the abbreviation, which seems like each component contributes to the overall test statistic. But isn't that what we saw when we ran stat test C? Let's just double check. Stat test alpha C, when you calculate that, hopefully I've got some, yeah. Went to, oh, I know where we saw that. We saw it when we ran a stat test D. Try that again, stat test alpha D. List 1 and list 2, when we calculated that, that's where we saw CNTRB. But that's not helpful because in AP Stats we call each one of these numbers components. But yeah, a lot of the components do contribute to the test statistic. But just be aware of that vocabulary issue. The vocabulary you're responsible for is the word component. If you add up all 4 components, you'll get 14.87. It's just one of them. And the p-value can come right off of the stat test C calculation that we did. So here's the conclusion. Since the p-value of it's low, it's less than 0.005, is what they said. They didn't report what it was, they just said whatever it is, it's less than 0.005. So we rejected null hypothesis. There's strong evidence of an association between having an epidural and subsequent success in breastfeeding. So the other handout that you had yesterday was the 14.3 handout. Please take that out, please. 14.3 handout. Or I'm sorry, the 10.3 handout. Okay, and in this one, in terms of interesting information and interesting problems to ponder, I just want to point out that in problem 29, the Montana problem, where we have a poll conducted by the University of Montana, classified respondents by which, or by whether they're male or female, and political party is shown. We wonder if there's evidence of an association between male and female. This is just a straightforward Titanic problem. It's because we don't have 2 samples. As Caleb summarized yesterday, he said, no, just 1 sample, 2 categorical variables, so we're definitely going for independence here. So chi-squared test for independence. The hypotheses, this is no new material here, this is just review. Null hypothesis is that political parties independent of gender, and the alternate hypothesis is that there's some sort of association. It's like women are more likely to be one of these or not one of those. So if you were to go through and actually type in the numbers, matrix B would give you the numbers after the slashes, which I don't even think it's worth it to write these down because you've done ones like this before. The point is, the reason you have to write down all 4 of the values, all 6 of the values of B is to verify that, to give yourself some credibility when you say that the expected cell frequency condition is satisfied because all the expected cell counts are greater than 5. But we draw the chi-squared distribution, it's not a bell curve with 4 numbers, it's a curve that kind of looks like this, skewed right with 1, 2, well, actually, you just need the chi-squared value and the p-value is all you really need. Because there is no observed value that's converted to a test statistic. There's just a test statistic. Just make sure you include your degrees of freedom there. And the conclusion is that since the p-value is fairly high, we fail to reject a null hypothesis. There's little evidence of an association between gender and political party. Where? On the whole planet? No, just in Montana. Question, page.
How do we get the expected values again?
They're in matrix B. So when you go to, on this problem, when you enter the matrix into the calculator, which I'm gonna pull up my calculator right here. Your very first move on the calculator should be to go to your matrix menu and edit matrix A. And isn't this a 2 by 3 matrix, 2 rows and 3 columns? So what is row 1 of the given information page?
36, 45, 24,
And row 2?
48, 33, 16.
Okay, so that's all you need to run a chi-square test for independence. Once you've got those in, then you do stat test alpha C. And you've already typed your observed values into matrix A. It's going to take care of matrix B for you, because once you calculate the chi-squared test statistic, which gives you a p-value of 0.08, then when you now go back to the matrix menu and you just press 2, enter, matrix B is there. Now it's kind of annoying because you have to see it, you have to scroll over. I would just round them to 2 decimal places, 2 or 3 decimal places. But using your right arrow, you should be able to scroll through matrix B. Those are the numbers which I think you can see are the ones that appear in my copy of the notes right here. And get that a little bit higher so we can see both at the same time. Sure, no, see 20.79, there they are, 19.207, it all came from matrix B. Does that answer your question then?
Yes, thank you.
All right, so next page. Next page, grades. Sometimes, you know, are grades really important? Does it really matter whether you get an A or not? Is it going to change your life? Well, you know, it's hard to say. Hard to say. Some people are concerned about, you know, different professors, different grades. And this is your classic 2 ships are sinking. You've got 2 samples. We want to know, are the distributions homogeneous? Does Professor Alpha grade harder than Professor Beta? Or are the distributions, I mean, do we have any evidence that one's a harder grader than the other? So it's like, here's the first ship that sank. We're looking at the distributions of A, B, C, D's, and F's for the Professor Alpha ship. It's like the Titanic, but we're looking at only one variable, which is grade. The other ship that sank is the Professor Beta ship. And the grades that came out were different. So I would like you to enter this 2 by 5 rows and columns, RC colon, 5 rows. So enter this 5 by 2 matrix into your calculator. Please enter the 5 by 2 and then calculate the values of matrix B and put those values in the blanks down below. So we're entering a 5 by 2. Okay. And all right, Kayla, would you give me the rows starting with row 1? Kayla.
Okay, 3, 9,
Okay, so the A's are 3 and 9.
11, 12, 14,
14, did you say 8?
yes,
Okay,
9,
It'll do.
2,
and
3, and 1.
alrighty, so Are the distributions homogeneous? We're running a chi-squared test for homogeneity. We have two samples, and we want to know if the distributions, is there enough evidence to convince the administrators that one professor is a harder grader than the other, or one's easier than the other? Well, mathematically, it's just a chi-squared test for independence, so we still do a stat test C. So stat test alpha C. We've already got our matrices in there, our values in for matrix A, so let's calculate this. P-value, ooh, borderline, 0.05. But wait a second, 4 degrees of freedom. Look at matrix B. Here's what a lot of students, they just skip it. They don't even think it's important. But when you look at matrix B, the expected cell frequency condition is not satisfied. Basically, the sample size is not big enough. Not all of the values in matrix B are bigger than 5. I mean, at 4.8, that's close, but 2.2, 1.7, come on. These are the numbers that they're asking you to copy down after the slashes. So go ahead and write down the values in that second matrix. You've got them on your calculator, so I don't need to leave them up here. The point is that you shouldn't launch the chi-squared rocket until you've checked conditions. So we have two groups of students, Professor Alpha students, Professor Beta. We're concerned with the distribution of one variable, grade. Grade is the only variable that's being distributed. We're performing a chi-squared test for homogeneity, not a chi-squared test for independence. The null hypothesis is that the distribution, notice the word same has to show up in the null hypothesis. Null hypothesis, we're just going to assume it's the same. This could be just natural sampling variation. So we're going to give the professor, in fact, who's probably being questioned? It's like, maybe they're upset at Professor Beta because he's grading too high. Or maybe people are upset at Professor Alpha because he doesn't give enough A's, too many F's. But either way, we're going to give them the benefit of the doubt that the distributions are homogeneous, if they're the same. Alternate hypothesis is that they're not the same, or you can use the word different, but then, whoa, put on the brakes, since the 3 cells have expected counts less than 5, the chi-squared procedures are not appropriate. Cells would have to be combined in order to proceed. So you might have to do put D's and F's together, and then maybe we can go forward. What's the DF rate? Somehow we've got to get everything up to be greater than 5. So the whole purpose of that problem is to say, look, we really do care about whether you check the expected cell frequency condition, that all expected cell frequencies have to be greater than 5. So I believe that concludes, yeah, that's the end of that. Let's go, I gave you some handouts for today. Let's go to the 10.4 handout. Hopefully we can locate that without too much trouble. This is the last chapter of the course. It says chapter 27. So, oh my goodness. Is it really true that we've reached the end? Good to it. Okay. Take out your AB80 chart. We need to fill in row 8. Okay, here we go. The last row of the AB80 chart is a one-sample t-test for regression slope. Let's take a look at what the parameter is. The parameter is beta 1. Let's do it like this. Let's go. We want to trap the true slope of the tangent line. Excuse me, the true slope of the line of best fit. Okay, so we got a scatter plot, and it's really just one sample. The scatter plot is itself a sample. And when Edwin Hubble was checking to see whether Einstein was correct about the universe expanding, because we talked about this, Einstein came up with the Big Bang Theory because it looks like the universe has not always been here. If the universe has always been here, then the sun would not still be hotter than the earth. Everything would be the same temperature. So Edwin Hubble collected data from 40 different galaxies. So it basically is a scatter plot. And what Edwin Hubble was up to was checking to see if Einstein was correct. So Einstein said that he looked at the redshift, and he predicted that the redshift would vary with distance that the star is, that the galaxy is. So Edwin Hubble did lots of work. He finally published in the year 1929. And basically he took 40 different galaxies. So imagine a scatter plot with 40 points. And Einstein said that the redshift will depend on how far the galaxy is. So it's like light. He said if the universe is really expanding, then when light comes from distant galaxies, it'll be like the Doppler effect. It's like the galaxy is moving away from us. So if the galaxy is moving away, it's kind of like a truck that's moving away. If the truck is moving towards you, so when the truck is moving towards you, the sound waves are being compressed and the pitch goes high. When this truck is moving away from you, the sound waves are stretched out, so it changes the pitch. So that's a shift in pitch when it comes to sound waves. When it comes to light waves, it's a redshift. So what Edwin Hubble did was he just wanted to check out, see if the universe is really expanding, to see if there's basically a beginning to the universe in the finite past. This is basically proving whether or not God exists, essentially. And for Einstein, this is the scatter plot that caused Einstein to reject atheism. It came down to a p-value. And so it's like, this is one sample of 40 galaxies. Believe me, there's a lot more than 40 galaxies out there. He just took a sample of 40 galaxies. And y hat equals b0 plus b1x. Now, if b1 is 0, then it's like Einstein was wrong. The universe has always been here. There is no God. But if b1 is not equal to 0, if there's actually a non-zero slope here, then that's an indication that Einstein was correct. So they assumed that actually the null hypothesis is that the slope of the line of best fit is 0. And the alternate hypothesis is that it's not 0. So it's all about, one sample of 40 galaxies might give you this line of best fit. Another sample of 40 galaxies might give you this line of best fit. Another sample might give you that line of best fit. We want to find the true slope of the line of best fit. What's the true beta 1? So B1 is a sample slope. Beta 1 is the true slope if we were to get all of the galaxies involved. And so that's why when you look at row 8 of this deal here, where I lost it. Oh, I found it. Beta 1. Beta 1 is the true slope of the line of best fit. And Hubble concluded that there really is a redshift, that the universe has not always been here, that the general theory of relativity is actually true. Einstein rejected atheism because of a beta 1 trap that Edwin Hubble was building. This all happened in 1929. 1929 is when it happened. But mathematically, oh, by the way, there's no way to do it on the calculator. So we're just going to give you the p-values. We aren't going to make you calculate them because there's no way to calculate it on the calculator. But the formulas, we will give you a B1, which is, B1 is the sample slope of the scatter plot. So here's the slope of the scatter plot minus, notice we're assuming the slope of the scatter plot's line of best fit is 0. We'll give you the standard error, basically the standard deviations of the slopes. It's like, we found one slope, but based on that one slope, we can calculate an approximation of the standard deviation of all the slopes. And then we'll use TCDF. Basically, it's a t distribution. It's not chi-squared distribution. It's not a z distribution, which we call a normal distribution. It's a t distribution. Okay, so how do you build a beta 1 trap? And what are the conditions? Well, surprisingly, there's 4 conditions. These are new acronyms for you. You'll love these. But look, the L-I-N-E, just remember line, okay? Like line of best fit, L, linearity assumption. You have to assume that the scatter plot is linear. So SEC is the straight enough condition. Have we done SEC before, the straight enough condition? Okay, so that's the linearity assumption. You might want to fill in that on the back. LINA is a linearity assumption, which is justified by the straight enough condition. The independence assumption, we've seen that before. Normal population assumption, nearly normal condition, outlier condition. Here's one you haven't seen before. EVA is the equal variance assumption. Basically, it can't, the plot can't thin out or thicken. Does the plot thicken ? Condition. Does the standard deviation seem to get narrow and narrower onto the scatter plot or not? So does the plot thicken ? Condition? You need to check all 4 of those conditions, or at least write about them, in order to do a responsible job with this. Yes?
What is AVA again?
AVA is equal variance assumption. So, yeah, question.
Do we check the 15,40 thing for NNC as well?
Yeah, I mean, they're basically, they're gonna give you the scatter plots, and
Okay.
and they'll give you the histogram, everything. So you won't have to actually do anything here. They'll give you everything you need to know to conclude just by looking at the data whether the nearly normal condition applies.
Okay.
Yes?
You might repeat a DTPT.
Yeah, does the plot thicken ? Condition? Yes, Bethany? Is the outlier condition, it's gotta be unimodal and symmetric, it's nearly normal condition with no outliers. Outliers are bad throughout all of AP statistics. Outliers are a problem. Okay, we'll wrap this up Thursday now. Tell you what, I'm not gonna have you do homework for Thursday, because we're not ready for that homework yet. I've decided to bump the test to Monday, but that means we'll have to do, there's consequences for that. Not bad consequences, but it's a domino effect. It means there will be some homework over the weekend for you, but,
Are we
I'll-
still having the quiz?
and the quiz is still tomorrow. Yeah, the quiz is just on chi-squared. So quiz Thursday, review Friday, test Monday. Have a good night.